Well, here we are. P3 to tonight? Okay. How are you feeling about it? No? It averages out. One comfortable, one not, one abstention. Okay, so short section, only one lecture on this. This is very short notes, and the reason these notes are so short is because I rely on the two papers by Balchi. And so we'll just talk about some basic terms: verification, validation, accreditation. What's the difference between those three? What's verification? What's validation? What's accreditation? How about accreditation? Is your degree program accredited?
Yeah.
What does that mean? Other people who are some kind of an acknowledged body of experts looked at what you're doing and said, this meets some set of criteria. So that's what accreditation is. It's an external body who hopefully has some expertise, and they come in, they look at what you're doing. Now, when would you do something like that? Let's say you want to make a simulation and you're going to sell it to the Department of Defense. They need accreditation. If you want to build hardware and fly it in an airplane or fly it on a rocket ship, you need to be an accredited supplier for that product, where they can trust that when your product goes on the airplane or the rocket ship, it's not going to cause damage to the rest of the system. And corporations and specific factory locations get like DoD approval. I am a DoD approved supplier of this product. Right? That's a form of accreditation. Within education, we have accreditation agencies like ABBY and SACS and ABET and NSA, CAE, and all kinds of different groups for different disciplines. And these are people who have expertise in the discipline, and also in the case of degree programs have expertise in education also. And so they're going to go through and say, okay, if you're going to call yourself a human factors program, thou shalt have these elements included in your curricula and certain processes to determine if you're actually achieving your goals, and on and on. And that's what becomes accreditation. Generally, accreditation is something that happens for a period of time or until major changes occur. So, for example, for education, since it's always a big deal for an educational program to be accredited, it lasts some period of time, 5 or 6 years, and then you have to go up for reaccreditation every so often. They want to make sure that you're still doing all the good stuff that got you accredited in the first place. If it's a product that's accredited, so if you say, you know what, I've got a simulation and it meets all these different standards, the different ISO standards or different mill handbook standards, that product would be accredited. But whenever you make a modification to the product, you have to work with the accrediting agency to see if you need to reaccredit, right? So there may be small changes that occur that still don't affect the overall product. And that kind of what can I change? What am I not allowed to change? That kind of thing has to be discussed or laid out in the accreditation documentation. So that's accreditation. Verification, validation. They're both some kind of test, which is which, right? You know the software world. What's the software world?
Am I building the right product? And verification is, am I building the product right?
Okay, so For validation, am I building the right product? How do you know if you're building the right product?
Is it what the customer?
Is it what the customer wants? Right. So in terms of software engineering, that's how they frame the terms. And then verification, how do I know if I'm building it right?
Does it meet its requirements?
Right. Does it meet the requirements? So the way software engineering works is you say, I have the customer tells me what they want, and we communicate with the customer long enough where we think we have the same shared understanding as to what we're going to build. What we're going to build is what they want. And that would be validation from a software engineering standpoint. Then once we all agree this is what we actually want to build, again, in the software engineering community, you start building a list of requirements. And the way you can tell that you built the thing right is you meet all the requirements. And generally that's done through testing. As we'll discuss here, there are many, many ways to achieve these things. All right, so that's the software world. Within the modeling and simulation world, you guys are building simulations. You're building a traffic simulation. You don't have a customer. So validation in the way we just discussed it doesn't make any sense. Similarly with the AV world, right? Even with fuzzy cognitive maps, if you were to use the fuzzy cognitive map to try to detail the drug interdiction example that they always use in the literature, you still don't have a customer. So what do you think you need to compare to for modeling and simulation validation?
The real world.
The real world, right. So in our context, validation means, does our model actually perform in a similar way that the real world systems do? So for example, with traffic simulation, for a long time, people still do. I just heard some person give a talk about some research they're doing now, and they're doing traffic simulation. And for a long time, people modeled traffic simulation like fluid through a pipe, and all the cars were molecules basically, and this was just fluid through a pipe. And what they found is that the validation wasn't that good. They were not getting real world results. And the reason is that drivers don't behave like molecules of a fluid. Drivers, humans, are irrational, right? We don't respond just to physics laws. We respond as agents. So people started modifying their traffic simulations to be agent-based, where each driver can make a decision. And as you know, if one driver makes a bad decision, we all have a bad day. Maybe we're not all going to the hospital, but we're all having a bad day, right? Because we're late for work and stuff. So those models achieved better validation. And those models are important. You know, there's a whole job called traffic engineer. And the job of the traffic engineer is to try to figure out, hey, how should you set up these traffic lights? How long should they be red and green on each side? How long should the turn arrows be? That kind of thing. I noticed Bevel, I get the names of the roads mixed up. Come off of I-4, the Bevel and Clyde Morris. And does anyone go through that intersection? Every day. I go through that intersection every day. I come off of I-4, Bevel, turn left on Clyde Morris. And it used to be that we'd all wait, right? The east-west traffic would wait, and then the east-west turn lanes would go at the same time while the straight traffic waited, and then the turn lanes would stop and the straight traffic would go. And now they've changed it where if you're heading west, the turn lane and the traffic starts at the same time. Then the turn lane turns off and the eastbound traffic starts to go. And then the westbound traffic starts and the eastbound traffic and the northbound turn lane go at the same time. I think what they're doing is they're somehow that within the same amount of time, I haven't done the math, but I think they're giving a longer flow to the straight traffic by doing it that way, I think. And then it's weird, in the afternoon, it flips where the eastbound traffic gets the turn lane first, and then the westbound traffic gets the turn lane later, once you get past, like, if you come in at like 1 or 2 in the afternoon. Why are they doing that? Somebody did a study. You've seen this where they have the cords across the road. You drive over it, bump, bump. What are they doing? They're counting cars. right? They're counting cars and they're figuring out what the traffic flow looks like. Why? All for validation. Now, what that implies with validation, since we're saying, does my model behave like the real world? We're implying we have real world data to work with. Now, you don't have real world data to work with. Alex is doing an experiment about future activities. You don't really have good real world data to work with. So I don't know, what are you going to do? You have to do things in a different way, right? Williams doing traffic study, you can find real world data. Now, it may be hard, right? It may be difficult, but you should be able to find real world data. Or go model an intersection locally, sit out there for 8 hours with your clicker, count cars, that kind of thing. That's for the fuzzy cognitive maps, what you have to do is model a simple system, and then you can see if the fuzzy cognitive map is mapping a real world system. But again, where are you going to get the real world data? All right, so that's validation in the modeling and simulation sense is, does my model actually represent the real world within enough accuracy where it's useful to me? Then the verification meaning is the same as it is in the software engineering community. Once I believe my model is correct, then I have to code my model. So think about the activity we've been doing the last couple of days. I keep talking to you guys about your model. We're drawing things on the whiteboard. We're not programming. We're talking about, hey, if this does this, right, how does it affect the values? What values do we want to model? What are the update functions to these values? How does the model operate? And by a model, I mean a mathematical model. Let me be very clear about what I mean by a mathematical model. A mathematical model is one that performs computation. Computation, by definition, there's always a fun discussion in other classes, but I'll just cut to the chase here. Computation, by definition, has no meaning. Computation, by definition, is mindless, literally mindless, rewriting of symbols using well-defined rules. Well-defined meaning non-ambiguous rules. So if I wrote on the board 1 plus sign, underneath it another 1, and in line underneath it, what would you tell me to write underneath the horizontal line? 2, because 1 plus 1 is 2, right? What does that even mean? It means nothing. It means I had a symbol called 1 and a symbol that I'm calling 1 and a plus sign, a symbol that I'm calling a plus sign, and somebody told you in the first grade that when you see that, you write down 2. It's computation. If I wrote two long numbers and said plus, what would you do? You'd start on the right-hand side. You'd combine those two numbers. If you have to carry the 1, you carry the 1. Are you thinking? No, you're doing. You're doing by well-defined rules. That's why we're bad at doing addition, because our mind drifts, we make mistakes, right? That's why computers are so helpful to us. They don't get bored because they don't have a brain. But the fact that they don't have a brain is also proving my point. It is a mindless activity. So that's what the model is. It's a mathematical entity where you're setting up symbols and providing meaning to them. Symbols do not inherently have meaning. You are providing meaning to them. Okay, I'm going to write a symbol on the board. What is that? Alpha. And what does it mean? Angular acceleration. No AEs in here. Angle of attack. It's the degree of certainty in statistics. Why does it have so many meanings? Because the symbol itself has no meaning. you ascribe meaning to it in the context in which you want to use the symbol. And by the way, we're calling it alpha. We could call it Bob, right? You're allowed to do that. Might confuse people, but you're allowed to do that. And there are times when you make up your own symbols. When you are developing your model, you will develop your own symbology, right? And you will develop your own operators, your own functions that modify the values of these symbols. So that's the model. Now you take the model, notice I haven't discussed programming at all, and you program the model. Is there an opportunity for you to screw that up? Absolutely. So what's verification? Proving to yourself that you encoded the model the way you intended, that you encoded the model correctly. And how do you verify that? Generally through testing. Generally. That's generally how we do software. However, as we'll see when we look at the Balchi papers, there's lots of different techniques out there. Okay? So those are the differences in those three terms. Verification, validation, and accreditation. Verification, did we build our model? Did we encode our model correctly in the simulation? By the way, sometimes you can't. Sometimes you have a model and then you try to encode it and you can't program what you wanted to, so you have to take a shortcut, or you have to modify your model somewhat, that kind of thing. Right? I mean, look at how many ways we talked about putting reaction time in the traffic model. Right? There's all kinds of ways that you can abstractly incorporate it. And so the trick is, did I effectively get the effect that I need in there, right? Then that would be a verification question. But the idea is, did I encode the model correctly? That's verification. Is the model actually useful? Does it represent real world stuff? That's the validation. Is it meeting some standards set by some other group of people? That's the accreditation. And by the way, this notion of, is the model useful, the validation question, there's a famous one-liner by persons whose name I forget. All models are wrong. Some are useful. All right, now let's look at this, some of the Balchi papers here. People write about these things. This is when is this? 2010. We'll go through some of this in a little bit. That's a chart that I found more annoying. This is my favorite chart in the paper. Okay. Informal, informal. What's the difference? Generally speaking. We also can use the same thing when we're talking about natural and formal systems too. But informal and formal. How would you define a formal system? All of you have taken MA 241. Is that a true statement? Calc 1. Is that a formal class? Is that a formal system that you're learning, or an informal system? Which is it? If y equals x squared, dy dx equals what? 2x? 2x? Any argument? How come you guys all came to the same conclusion so quickly? Did you think? You didn't think. What did you do? You used a rule, right? A formal rule, a formal and non-ambiguous rule that applies in all situations like this, right? And the formal rule is, you take that, you put it down there, and then you subtract 1, right? Technically speaking, I should have written it like that with the 1 there because it's there, right? So you guys followed a rule, a formal rule. And that's how that entire class was built, is teaching you the rules. That's a formal system. And when we say formal system, that's what we mean. A mathematical system that works on symbols and rewrites the symbols based on non-ambiguous rules. Can't argue them. Now, what do you think is going to be informal? You get to yell and scream and holler and argue about what the right thing to do is and whether this is a good idea or a bad idea, right? We're writing some reports right now, and we put some web links in our report. And then someone just sent an email last night that said the rules are you're not allowed to put web links in the report. And I expect that we are going to have a huge argument about this because that is not a formal system. It's an informal system where the preference may be not to have links, but everybody in the past has always had links. So why would we change it now, right? So informal system. The way this works in the real world with informal systems is you're working with a group of people, and generally you can do things like reviews and walkthroughs where you go into a room of people and say, here's what I want to do. What do you think? And these people who are hopefully experts in the domain will say, oh, that seems reasonable. Maybe you could change this. This is crazy, don't do it, whatever the feedback is. So the past couple of days I've been working with you guys. We've effectively been doing reviews and walkthroughs because we're talking about, hey, how are you going to model your system? Show me what you're going to do. I give you some feedback. None of that was formal. That was all informal because it was all based on discussion, opinion, best practices, concepts, right? How we might frame things, that kind of thing. Audits and inspections are similar, and then checking documents. So you want to check if somebody says, oh, I need you to simulate this widget. Okay, you need to go to the documentation of the widget to find out how it behaves. Right? So what I'm saying, when you want to get acceleration for vehicles, go to the specs, right? That exists. You're going to check your document. And then as I'm reading through your reports that you're building, I'm checking your document there. I'm not sure what face validation is. Inspections and audits, though, those can be inspections and audits of the requirements, of the model, of the software itself. Those are normal things. If you're in the software engineering community, those are normal things to do. If you're in the simulation, computer modeling and simulation community, by definition, you're in the subset of the software engineering community. And then in formal systems, we actually can get away from the code and get into proving things through analysis, proving things through logical proofs. So induction is a form of logical proof. Are you computer science? Have you had CS222? Did you do proof by induction?
Yeah.
What semester are we talking about here?
My second one.
No, I mean, like, this is summer 2025. Was it spring of?
Spring 23.
Okay. Okay. If you was one thing you remember from that class, induction. If you don't remember induction, go back, relearn it, because 20 years from now, that's still going to be a useful tool. Lambda calculus is a form of computation that was developed by Alonzo Church in the 1930s. And basically what he wanted to do was develop a notational system that would cover all computation ever. And he developed a very simple, straightforward system that covers all computation ever. It's highly notationally dense, but very useful. Logical deductions, predicate. These are kind of different versions of saying logic, right? Predicate calculus, predicate transformation, proof of correctness. Those are all varying subsets or degrees of logical Boolean logic. All right. So you can do your verification and your validation by run your software and then compare against the real world. That would be validation. Or have some series of specific test cases and run your software and prove that the test cases pan out. That's your verification. But sometimes you can do verification by analysis. So for example, in computer science, we talk about algorithms quite a bit. And an algorithm is a process by which a problem gets solved. So, a common algorithm is the quicksort, which is quicksort algorithm is a way that you can sort numbers in a quick amount of time, hence the name. And that algorithm wouldn't be any good if it didn't work sometimes. But there are proofs, and they're not hard to make, there are proofs that quicksort works all the time, right? It was proven. We haven't checked every possible list of numbers because that's an infinite set, right? So we can't, but we can prove that it will always work. So that's how you can get away with doing some formal analysis. I do not expect anyone in this class to be doing formal analysis. All right. Alex is going to be closest because she's got stuff that doesn't exist in the real world. But what she's doing is she's going to the sources and saying, look, this is a specific vehicle that I'm interested in. Here's the specs. This is a specific rule that I want to use for traffic. And here's what the current FAA roadmap says the rules should be. So she's doing a form of validation by using other people's beliefs as to what the reality is going to look like when this reality occurs. Okay, then static and dynamic. And static and dynamic are terms that are used, again, frequently in the software engineering community. Static means anything that you can do by looking at the program, by looking at the code, but not executing the code. Dynamic means anything that you can do by executing the code, or anything you can only do by executing the code. You look worried. You okay?
No, I'm just trying to take all this.
Okay. So how do we do how do we do testing? So again, in static testing, you can do some structural analysis, right? In the static stuff, we did start talking about how are you going to code this yesterday and the day before. So if we start talking about how are you going to code this, then what we're going to do is look at the code. Like yesterday, William showed me his traffic model, and he showed me some code. That was a static analysis, right? We were doing a walkthrough basically of your code. And the reason it was static is because we didn't run the code. When you made your hello world scenario and ran the code, that was a dynamic analysis. So with static, we can build state diagrams, we can build context diagrams, we can build communication diagrams. All of these are things that explain how the system is going to work without actually running the code. And there are some highly evolved formal systems that allow you to do what is currently called model-based quality assurance, where you build if you're building a software product, even a simulation, you actually build a model of that software product. So think how meta this is. You want to build a simulation, you have a model of the real world. You want to encode that model of the real world in your simulation. Now you can build a model of your simulation to try to convince yourself that you're building things right. Okay, so data analysis is pretty common. I think that if any of you have taken, when you guys took your first programming courses, they tend to talk to you about the flow of the program, and they tend to talk to you about the flow of the program. How many of you guys had to build a flow chart? Anybody have to build a flow chart? That was generally a control flow chart, meaning we start here, we do this, we have an if statement. If it's true, we do this. If it's false, we do that. In other words, you're doing the flow of the control of the program. You can also do flow of how does the data move through the program. Oh, we assign to X here. That value gets used down here. That value is reassigned down here. So you're tracking how the data moves through the program. So we can track through flow analysis and control flow analysis and data flow analysis. We can just look at how is the program going to behave and predict how the program is going to behave without even running the program. There are tools out there. In fact, does anybody use Eclipse for writing? And I think, what's the other one? CS350, the Microsoft one. VS Code, yeah. Both of those will do the same thing, which is if you take a line of code and you say, hey, show me every line of code before this that could potentially affect this line of code, then it'll go backwards through the program and find every place that might potentially affect that line of code, which is very helpful for debugging. But notice that's a static analysis. You didn't run the code. It's just looking at the code structure and identifying what data values can flow to that line. Right, so control flow analysis, that's when you did your flow diagrams. Data flow analysis, you probably, hopefully you were did at least one exercise in an early programming class where you took a variable and you said, after this line of code, this is the value in that variable. After this line of, at the next line of code, this is the value in that variable. And you did what's called tracing, where you trace the value and how it changes as the program goes line by line by line by line by line. You don't do it for big programs by hand because it's, you know, a mind-numbingly tedious task. But the idea is you're still tracking that. That's how you do debugging, though. That's how you convince yourself that you've got that right for the static stuff. For the dynamic stuff, you're going to do testing. Acceptance testing assumes it's a product, right? Acceptance testing assumes that you're selling something to a customer and they're not going to accept it until it passes acceptance tests. And this is a term that's used for both hardware and software. So for example, back when I was in industry and we were building satellite components, we would receive avionics boxes from vendors, and before we would accept them, they would run through a series of tests, acceptance testing. Then we would accept them, incorporate them into our product, and then we would run a larger scale acceptance test before we could ship it to NASA. Acceptance testing tends not to be that rugged, particularly in the physical world. When you're talking about physical parts, you do different kinds of testing. While you're developing the system, you try to break it. Right? The job is to see what the limits are. So you keep pushing and pushing and pushing until it breaks to find out what the limits are. Clearly, you can't break something you're trying to sell to somebody, right? So what the acceptance tests do is they back off from that extreme and you run the system through whatever tests you need to, but once it passes acceptance testing, then it'll go through. So within the context of software, your acceptance testing is, again, going to be a suite of tests. Look, here's some scenarios. We know what the outcomes are. So we run these scenarios. Here's the outcomes. Or maybe down at the function level. Here's the inputs to a function. We know with these inputs, this function is going to produce this output. So here's the inputs. Here's the outputs. The function is working correctly. We will accept it. If you're dealing with a system that has both hardware and software, then you also have to test the hardware portion, which means you generally run it through a bunch of physical tests. And the colloquial term generally is called shake and bake, because typically what you do is you put it on a giant vibrator and shake the hell out of it and see if it can survive. Again, aircraft are vibration, right? They're full of vibrations. Helicopters have a lot of vibration. Spacecraft for 8.5 minutes have a whole bunch of vibration. So you need to make sure if you've got an avionics box on a spacecraft, then you have to survive this 8.5 minutes of just really tough environment. We've got a bunch of CubeSat programs going on campus. I promise you, go find somebody working on CubeSat, and they're going to talk to you about the launch environment and how difficult it is to get through the launch environment, because that CubeSat is going to be shaking like crazy during launch. Once it's up there, no problem. But then what happens on orbit? What do you have to worry about? What's the environment up there like? Radiation. So you have to be radiation hardened and EMF hardened, hot and cold. So it's called shake and bake because the shake part is you put the thing on a shaker and shake it. The bake part is you put it in a thermal chamber, pull a vacuum, and then you make it hot and you make it cold and you make it hot and you make it cold. You know, you run it back and forth for a while and make sure that it still operates. And again, if you look on different specifications, you know, if you're going to meet, again, a DoD standard, typically it's something like your avionics has to be operable up to 120 degrees Fahrenheit, and it has to be able to be stored up to 150 degrees Fahrenheit, and then still be able to operate after it's been exposed to that. These things are out there. Right? Anyway, the dynamic aspect of acceptance testing is you set up this suite of tests and you try to run it. Alpha testing, we've heard of the alpha beta testing, alpha and beta testing. So beta testing is the one that gets all the advertising, it seems. And what's that about? Beta testing is when you're sending your product out for people who did not develop it to use it. So beta testing of a game is you just put it out there and let people play the game, right? They didn't write the code, they didn't develop it, they didn't come up with the game. They're just people who hopefully will be customers one day, and they're going to play with the game. Alpha testing is when the people who are actually in the in-group are doing the testing. So there's a little, you can get some like confirmation bias in there, right? Because we already know how this thing is supposed to work. But the bottom line is you're testing a product with the understanding that those test results probably will come back to you in the form of, we need to modify something. Bottom-up testing is when you're testing at the component level, and that component, you know, everything is a system, right? So you have components that get put together to create another component, and then that gets put together to create another component, that gets put together, right? So you start down at the lower levels testing, and then as you start to integrate, then you need to make sure that they work together as a whole, but you still might do testing to make sure the component works. In software testing, the way that that's often called regression testing. So if you build a little function or you build an object, and now you're in an object-oriented world and you want to put a couple objects together, you have to make sure that by putting them together, you didn't screw anything up. So you test at the system level, right, at the higher component level. But then the regression testing would be you go back and still do your testing of the individual components again. And in the software world, and you want to do that with automated systems. Most software development systems today are complex enough that you have a repository where the software is kept. If you want to modify the software, you have to check it out, then you modify it, then you check it back in, you do something like a merge so it goes back into the baseline. And at that point, you can set up these systems in such a way that it will run a suite of tests on the software to make sure you didn't break anything. Compliance testing, what does that imply? Complying with what? Generally, that's going to be, again, like an accreditation thing. You're complying with some external rule. You may be complying with some self-imposed requirement also. Avionics has to run on 28 plus or minus 4 volts. Okay, to make sure that whatever we put out doesn't exceed 28 plus or minus 4 volts. Okay, that would be compliance, right, with the rule. Performance testing, what's that going to look like? What does that mean? How fast it runs and how much can it handle, right? So usually performance is, yeah, how efficient is it? And then you can scale things up. Like with traffic, we have to worry about performance. If I want to do traffic over a one street with two intersections, I probably don't have to worry about performance. But what if I want to do Manhattan? Okay, tens of thousands of vehicles, tens of thousands of intersections, and now I want to make sure that it's computationally efficient. What if I want to do a human in the loop simulation? Like a pilot, right? With pilot, we really have to worry about performance because the reactions have to occur in real time. This can be a real issue with military simulations. So with a military simulation, you might want to have your goal of having two or three brigades, armored brigade and infantry brigade and whatever. And so now you've got hundreds and hundreds of entities participating in this virtual landscape. And so you want to make sure that in the virtual world, when I say something happens, it happens without lag. It happens right away. The gaming world worries about this. When you go in and do an online game, they're going to plunk you onto a server and they limit how many players can be on each server. If it goes over that number, they start putting them on a new server, right? So you're in these different virtual worlds. What's that about? Performance. If they get too many players in one server or in one set of computers, then the lag starts to show up, and then they have an issue. You're also going to hear about if you pay attention, if you pay attention to the right places. Before an election, you might hear about performance because they'll take the voting equipment and the tabulating equipment, and they'll simulate just bunches and bunches of people voting, and then run the tabulation and make sure that they can handle everything. And I only know about that because there was about 6 years ago or 8 years ago, there was this big thing in the news. Oh, all the voting equipment's no good because they failed their performance test. And it was like, no, if you know what you're talking about, if you actually know testing, everything's fine. Calm down. They just had a particular situation where they were, I think, actually mistesting. Right? They weren't testing appropriately. So anyway, be aware these things are out there. Once you're aware of them, you can hear about them in different news items. And if you're really aware of them, generally you'll see if it's a real histrionic news item, it's usually not as bad as the news item is saying it is, usually. Execution testing, doing the execution, fault failure insertion testing, where you deliberately inject issues. Why would you do that? Why would you inject wrongness?
Your error handling.
Yeah, one of the things you want to find out is what happens when things go belly up, because you always want your software to be in a controlled state. Now, I'm assuming the whole system is software here, but simulations can be software. They can be software and hardware mixtures. But yes, you always want your system to be in a controlled state, which means that even when it's failing in a controlled fashion. Right? We call it graceful failure. When one of the things that the power strips do, the surge protectors do for desktop machines, is if the power goes out, you have a short amount of time in which you still have power, because there's like a capacitor bank in there that'll still keep power to the computer. Enough time for you to save your work before everything gets shut down, right? So the days of having, I had a power glitch and I lost all my edits to this document, those days are harder and harder to create, right? That used to be a fairly common occurrence. And so now there are ways around that. One way is that Microsoft is always saving your documents, right? Locally. And so even if you get an issue, you can go back and find that marked up document and use that as use it as a recovery. That's a way to do to recover from failure. Well, how do you verify that works? pull the plug on your pull the plug on your machine, see what happens. Right? Inject a failure. So as you can see, we have a lot of objects. We're going to deal with statistical techniques, right? How do you verify against the real world? Well, if you run it once, that doesn't mean anything. So the way I'm encouraging most of the simulations in this class to work is that you run them a bunch of times and then you do statistics on the results. Well, the same thing is true if you're going to do verification or validation. You can't tell from one run, so you run it a bunch of times to make sure it works. I want to make sure my traffic study works through a specific intersection. I pay someone to go tell me what's happening at that intersection, and then I run run that scenario 50 times. And on average, did I get what they measured in the real world? Oh, and in the real world, maybe they're out there for 2 weeks and they average the results too. Structural white box testing, and that's more of a software term. In white box testing, you know what the structure of the code looks like. So you're able to take advantage of that and test very specific things. Generally, you're going to test very specific if then else conditions, make sure you got those right. You're going to test function input output, make sure you got those right. You're testing little tiny pieces of code generally. As opposed to black box testing, you don't know what the code looks like, but you know what the behavior is supposed to be from the requirements. So you just inject some inputs and see if the outputs come out. Even though you don't know what's going on in the middle, you know what the behavior is supposed to be because it's defined by the requirements. Stress testing is where you're trying to test the thing to the limit. So again, you're saying, you know what? I think this thing can. I think the simulation can handle 300,000 agents, and so let's put in 300,000 agents and see if it really does, right? That kind of thing. There was a group. How did it work? There was a group that wanted to do set up a scenario as a proof, just as a proof of technology, that they would set up a scenario and that was a military simulation, and the scenarios were all like individual soldiers and individual vehicles, so very, very low level. And they wanted to have 100,000 entities active at the same time, and it was a real-time simulation, right? So they wanted to have 100,000 entities. And they published a paper that said, here's what we're going to do. We're going to have 100,000 entities. Here's how we're going to do it. Then the next year they published a paper and they said, okay, we haven't done it yet, but we're building the parts and we think we can do 40,000 entities. And then the next year they published and they said, we did it, but we could only get 8,000 entities. So, and still maintain real time. That was stress testing, right? They were testing the limits of how much they could do there. And by the way, the thing that limited them was in order to do that, they had to use multiple processors, and the processors all had to communicate with each other, and it was the communication cost that moved them from 100,000 to 8,000. Because it's an n squared communication cost. Okay, so bottom line here, be aware of these categories. Within the categories, you should be aware of at least one or two different kinds of things that are pretty common. So in an informal sense, the reviews and the walkthroughs are really common, right? That's what we've been doing. That's what I encourage you to do with other people, right? Show other students in your class, or show your roommate or something. Hey, here's my model, here's my code, here's this, right? What do you think? The formal stuff is anytime you're dealing with mathematical, and I think you know what I mean by that now, a mathematical mechanism to try to do analysis on your model. or on your simulation. Proof techniques, formal systems. There's a no, we'll get back to it. And then the difference between static and dynamic. So static, again, is while you are just looking at your code without operating it. Dynamic means you are executing your code. So there are certain things you can do to the static code. Just read through it. Do your flow analysis. And certain things you can do dynamically. Set up a scenario. You know, initially, some of the first things you should be doing when you're writing your code is you're going to do this informally, but I'm sure you'll do it, which is, you know, does it work? I don't know. I want to write a stupid, simple scenario and see what happens. So William's got this square traffic pattern. It's a simple scenario, just to see what happens and for him to learn the system that he's using.
Right.
Yeah, absolutely.
Starting small is the way
You have to do it that way. Yeah. So fuzzy cognitive maps, 2 nodes, right? Or 1 node that loops to itself, or 2 nodes that loop back and forth to each other. Stupid, simple stuff. 1 vehicle with no intervening heliports, right? Just here to there. Then you can let it go stepwise, right? Things like that. But be aware of just these categories. Then this table, these principles, V&V must be conducted through the entire M&S life cycle. Well, what the heck is the M&S life cycle? Well, it follows the engineering life cycle, right? So you start out with a needs statement. You start out with either customer needs, or as a researcher, you have a need, and then you're going to develop some requirements based on that. Now, again, depending on your discipline, if you're a software engineer, you're going to go heavy into requirements. If you're not a software engineer, you're still going to have some kind of goals for the simulation, which become requirements. Then you do a design, which we've just gone through. Then you do your build, which you're going to be doing now. And then you do your testing, and then you actually do the experiments, the simulations. Now, again, from there, it depends on what the product is. Is this a training system? Well, then that's going to get deployed, and it's going to get exercised over and over and over again by people being trained. Is this a research project? Well, you're probably not going to deploy it anywhere. You're going to use it. You're going to do your research. You're going to publish. And then what happens? You may never see that product again. There is a long and shameful history in the field of research in academia where we keep creating all these expensive pieces of software, and then they just rot on the shelf. And whoever needed them graduated, they got their PhD, right? They used it for their dissertation, they got their PhD, they went away. And so they're the only ones that knew about the software, and they're gone. In a really well-developed research program, people try to scaffold where if one student or one set of researchers builds some software, then we do the work properly and keep the documentation. And that way the next group of people can come in and pick up where we left off and keep continuing the research. It's very difficult to do, and so it's hard to pull off. But the point is V&V conducted throughout that entire life cycle. Well, what does that really mean? Early on, you start thinking about verification and validation. Early on, you're going to start creating your model pretty early. That's an opportunity for validation. You can exercise your model by hand before it gets turned into code and build a simple model. Do it by hand. See if you think the results are reasonable. That's early on. If you wait till you built the thing and it doesn't work, you've wasted a lot of time. So verification, validation throughout. Similarly, as you start to build the model, You can do verification on the model itself, right? What happens if we throw this at it? What happens if we throw this at it? Does it work the way we thought it should work? Then when you start building out the code, you're doing the same thing. The outcome should not be considered as a binary variable or model where the simulation is absolutely correct or absolutely incorrect. Why would that be? That's a weird thing to say, isn't it? They're saying you don't have to be right, meaning 100% right. Yeah.
Well, aren't models themselves not perfect?
All models are wrong. Some are useful. So what we're accepting is, yeah, of course it's wrong. Is it close enough? Is it good enough? And then you can make decisions. If it's not good enough, then we can change it, right? We can make it more correct. It will never be absolutely correct. And again, typically you're dealing with statistical situations anyway. Typically. So what you're trying to assess is, did we design it well enough? Did we build it well enough? Is it still useful? And you'll hear this, again, if you pay attention and people are honest about their work, they'll say, these results, how do I want to say it? These results correlate to a real world result. What does that mean? In the real world, if the trend line is up, our trend line was up too. We were off, right? We were offset, but they went up in the real world. We went up in our simulation. We correlate. We're useful. And so what you can do with a simulation like that is you're saying, if I want to study how, factor X affects output Y, I'm still getting the right trend line. I may not know the exact value. I'm getting the right trend line. You see this discussion with I think most in the real world right now where you're seeing this discussion is with the global warming or climate change discussion, because if the research doesn't nail the 2026 maximum temperature right on the head, then the critics will say, see, you don't know what you're talking about. Right? Well, is the trend line there? That's what you want to pay attention to. Simulation model built with respect to M&S objectives and its credibility is judged with respect to those objectives. In other words, we've talked about this before. Every model is an abstraction of the real world. Every model will absolutely not contain some things in the real world. It may contain things in the real world and get them absolutely wrong. But if that's not what you're using it to study, you don't care. What you care about is, look, I'm building this model to study these 5 things, and these 5 things work. Those are my objectives. So I'm gonna judge my model with respect to the objectives. We've got these really expensive aircraft simulators. How many passengers do they hold? None. But nobody cares. That's not the objective. V&V requires independence to prevent developers' bias. Now, quite frankly, that's not going to happen. Who's doing the V&V? The person building the system. They are implicitly biased. Now, here's one way where you can get it. When you do the walkthroughs, there's actually a distinction here, and I can't remember the distinction. There's a distinction between a walkthrough and an inspection. And with one of them, you take people who are outside of your group and bring them in. I recommend in both situations, try to get somebody from outside the group and bring them in, because they're going to come at it with an unbiased eye. You actually want them to be a little antagonistic. That's where they're the most helpful. You want them to be a little bit of a jerk. That's where they're going to be the most helpful. And then they'll say, oh, okay. Here's good, here's bad. But the idea is you want independence view. There's another issue here that I encourage students to try to develop, and that is to try not to put any of your ego in your product, right? So you're like, oh, I built this, it's so cool, and somebody comes and criticizes it, and then you may feel like they criticized you or your baby, right? And you need to learn to let that go, okay? And the reason is, if people are coming up with valid criticisms, what are they doing? They're improving the product. They're making it better. And if you remember that, oh, okay, this person, pointed out a place where I screwed up, which makes me feel bad, but they are improving the product. So I want to focus on that. I want to take it from there and take your ego out of it. Then it helps a lot. You produce better product that way. And that's true anywhere, writing, all kinds of places. VFB is just difficult and requires creativity and insight. There are people that will argue against that. So one of the reasons that the formal systems aren't used very much is there's a perception that they are overly difficult and add way too much cost compared to the benefit. And so the people who are really into formal V&V systems try to push back against that and say, no, if we develop some tools, and some tools are being develop some tools, it makes the time effort go down. The difficulty is not bad. And that's true. If you have an engineering degree, you should be able to understand the mathematics that's going into a formal system for V&V, because it's not that bad. It's not that hard. Credibility can be claimed only for the prescribed conditions for which the model or simulation is verified, validated, and accredited. What does that one say?
You can't truthfully use it outside of what it's been designed for?
Absolutely, yeah. You built this model with a goal in mind. And you made sure that the model actually worked for the goal. Now someone else is going to come along and say, hey, I heard you have a model for X. Let me use it for this, crazy thing that you never thought of. Oh, okay. I've got a great model for an aircraft where I can determine the maximum temperature on the leading edges at altitudes and speed. Cool. Let me use it for fuel consumption. It's not in there. There's no fuel. There's no fuel in my model. Let me use it for pilot vision. Yeah, not in there, right? Complete simulation model testing is not possible. By complete, they mean every single aspect. And again, we've even seen just in the experiment world that generally doing a full suite of experiments is not always feasible. So what they're saying here, and again, this is a corollary in the software engineering world, there is no way you can fully test a large piece of software. No way. And the same thing is true here. With a simulation of even moderate complexity, it is infeasible to try to fully test it, right? Fully test for every possible input. That's what we mean by that. There's an infinite number of inputs. I mean, look at your simple math. You can create an infinite number of car scenarios for your 4-road model, right? So already you're in that realm. Right? VV&A must be planned and documented. And again, this is where, because a lot of modeling and simulation happens in a research environment, in an academic world where you're supporting grad students, and the grad students are trying to get their thesis out the door so they can graduate, that documentation, planning and documentation often falls by the wayside. In the commercial world, it depends on the contract. If the contract says, we're not going to pay you unless you give us this document, then you're going to get the document. But if the contract doesn't say that, even in the commercial world, I'm going to tell you, the documentation won't exist. I've worked with some commercial software systems that were very large, very well funded, and the documentation was just utter garbage. I mean, literally, we were reduced to just searching the code for what we wanted to find, rather than try to go to a document. Because it wasn't part of the contract. Oh, and by the way, you got to deliver by June 10th. right? Okay, if you got to deliver the product and your money depends on the product, not the documentation, you're going to make sure the product is done. Type 1, 2, and 3 errors must be prevented. Oh, we'd have to go back and look at what those things are. I forget what they are. They may be categories of severity. Errors should be detected as early as possible in the M&S life cycle. Now, by errors, what this person really means is faults. And in a technical sense, the error is committed by the human, and by having an error, the human injected a fault in the product. And so this line technically should read faults, but that's a difference between, again, a modeling and simulation person talking and a software engineering talking. So the faults should be detected as early as possible. And this is always true in software. You should always find the faults as soon as possible. It's a cost benefit thing. The longer you wait, the more expensive it is to fix. And sometimes the longer you wait, the more rework you have to do because you built other stuff that has to be changed because of the fix that you had to do for the fault. Multiple response problem. We have to go back and read through what that is. This is the if you have a situation, a scenario where you're looking at multiple outputs and some of them are right and some of them are wrong, I believe, if I remember correctly, then you have to resolve that because you need all of them to be right at the same time, obviously. Successfully testing each submodule does not imply overall module credibility. So if you test all the submodules and then you put them together, then that's not a guarantee that the whole system is good. And this is true. It's actually been proven. My PhD advisor published a paper 15 or 20 years or so ago with a similar process. There's a group of people called component-based software design. Component-based software design says, hey, if you have these components, you can stitch them together and then you have a working system. We see that nowadays with Python because everybody's like, oh, I'll just grab this library and put it together and my system will work just fine. It's provably chaotic in the mathematical sense, though, that if you take things that look like they work well individually and put them together, that there may be interactions, emergent interactions that make the overall system not work right. And it might work right most of the time, but there might be some what we call pathological cases where it won't work. You kind of know this because how did we start out this course? We started talking about agents and we talked about how you get interesting behavior through agent interaction and you get the emergent behavior. Well, if you think of each submodule as an agent and you put them together in a system, now you've got submodule interaction. They're all acting like agents interacting. And so you get emergent behavior. And what do we know about emergent behavior? It's hard to quantify, it's hard to define, it's hard to know where the boundaries are. It is not very predictable. So again, there's no guarantee just because it worked well, just because the submodules work, that the larger system will work. Double validation problem. We need to read back on them. I'm sorry, I didn't have time to read this paper through again before today. Simulation model validity does not guarantee the credibility and acceptability of simulation results. Okay, so what are they saying there? Simulation model validity, in other words, it's a valid system. What does it mean to be valid? It means that it actually does match real world. Does not guarantee credibility and acceptability of simulation results. So, what does it mean to be credible? You are
meeting like.
It's not accreditation so much. It's credible. If you said what I'm saying is credible, what does that mean?
You can trust it.
You can trust it. You can believe it. You can believe it. So you can have a simulation model, and it might be valid, but that doesn't mean anybody will believe you. That's what that's saying. Do not expect that people will believe you. People are weird. We are not rational. The opposite can be true. How many times have you heard, oh, so-and-so run a computer model and here's the results they got. And so everyone's like, okay, that must be true. Well, you know better, right? Hopefully you knew better before this class, but you definitely know better now. If the model was invalid, if the simulation was invalid, they might have run a computer simulation or run a computer model, but the results may or may not be true. Right? But even if you are true, you can have the problem, the reverse problem, where people refuse to believe you. They will claim that you are not credible. And again, the biggest real world example of that going on now is with climate change. You've seen that for decades, where people are saying, huh, here's our model. And then a bunch of other people are like, we don't believe you. And then the acceptability. What is it? What is an acceptable result? Good news, right? But it may be that your model is valid and the results are not acceptable. And there's two ways that you can frame that. The one that I'll focus on is was it good news? So somebody hires you, right? A company hires you and they're like, okay, we want to sell this product out in, we're selling it in Virginia. We want to see if it'll sell all across the US, right? We want to go national. And so you do some kind of a simulation and blah, 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 blah. And then your result is, sorry, the only people who's going to buy this product live in Virginia. That may not be acceptable to your customer. Because that's not what they wanted to hear. It may be valid, you may be right, but that doesn't mean they're going to accept it. Or it doesn't mean the result is happy. There's a logical fallacy. Oh boy. There's a proof by authority. That's a logical fallacy, where there's an authority that says X and therefore X must be true. That doesn't always work. Sometimes authorities are wrong. There's proof by tradition. We've always done it that way. That doesn't mean it's right. There's proof by popularity. Well, everybody thinks it's a great idea. That doesn't mean it's a good thing, right? And then there's also, I can't remember the term, proof by consequence or something like that. Why, that can't be true. If that was true, look at all the horrible things that would happen, right? So people will say, frame as a logical proof, this thing can't be true because all these horrible things would happen. Well, you know what? If the proof is true, the proof is true. If the model is valid, the model is valid. So what you might find is, okay, we've got a simulation model of infection rates of this brand new disease, and according to our model, half the people in the US die. Well, that can't be true. Look how awful that would be. Well, it may be. Maybe we should do something about it, So that's what that is talking about. Just because your model is valid doesn't mean people are going to want to hear what you have to say, basically, is what that's about. Doesn't mean they're going to believe you. Again, perversely, there is a reversal of that, which is, again, if people have a magical belief in computers, right? People who don't understand computers have a magical belief in computers. And so if somebody says, oh, I did a computer study and here's my result, the average person is actually more likely to believe them without knowing anything about the underlying computer model. Now, you guys know by now, if the model is garbage, right? If the simulation is garbage, if it hasn't been validated, then the results are garbage. But people have, because they have a magical belief in the computer, as soon as you say we did a computer study, or now the modern version of that, I asked ChatGPT and it said X, therefore X must be true. But as you know, people keep getting in trouble for using that. Because the first big example of that a few years ago was a lawyer that was submitting documents to a judge and they had a bunch of references in it and all the references were made up. ChatGPT is a pattern matching machine. And so it matched the pattern. Oh, this is what a reference looks like. And so it just made them up. And the lawyer didn't verify it. And I damn near got sanctioned. Should have gotten sanctioned. Okay, and then a well-formulated problem is essential to the acceptability. Okay, so why did I start you out early on with your research questions? Why was I trying to get you to frame that the very first thing? Because as we keep saying, a simulation model is not 100% representation of the real world. There's the real world. Then there's that thing we call the referent, which is the measurement of the real world. Then there's the model, and the model is only going to contain what's interesting to you as a researcher or as a trainer or whatever your objectives are. So it's only going to contain the stuff that's interesting to you based on your objectives, which means you want to be really, really clear about your objectives before you start. So that's why well-formulated problem. Here's the question, here's the hypothesis, and when you guys turned in your stuff, I was looking, I gave you comments back on your research questions, right? Oh, we need to reframe this a little bit. Okay. Read this paper, it is good. And there's two by Balchi in there. They're very similar, as I recall. Are they the same paper twice? No, okay, there you go. There's a lot of overlap here, but these different, oh, good, we can find out what type errors are. Right? So yeah, read through these principles. That's good stuff. Okay, do we have questions? I'm going to stop the recording. First, I'm going to stop. Okay.